Hi, everyone. My name is Michael Hicks. I'm a professor at the University of Maryland. And today I'm going to tell you about some work that I did with my collaborators at Maryland on the Build It, Break It, Fix It security-minded programming contest. Now, we're all familiar with the two sides of cybersecurity. The Build It side, whose goal is to design and implement a computer system in a way that prevents security defects. And of course, this is a heavy emphasis here at CSF. And also the Black Hat or Break It side, which aims to find defects that constitute vulnerabilities and to exploit them. Now, a problem you may have observed is that there's quite a bit of emphasis in the community writ large on the breaking side of things. And you can see this as evidenced by the various capture the flag contests and security challenges. They tend to be about breaking stuff rather than about building it so that it can't be broken. So a few years ago, we decided to try to rectify this problem by designing a new programming contest whose aim is to reward those who know how to build systems securely rather than only break them. The contest is set up as follows. It has three phases. First is the build it phase, in which participants build a piece of software according to a specification. The next phase is the break it phase, in which participants have access to each other's submissions, and they're able to try to find and exploit vulnerabilities therein. The last phase is the fix it phase, in which teams that originally built submissions are able to try to fix bugs that were found by their fellow participants. At the end of all of this, the judges tally final results and declare the winners. There are two scoring systems. One is the Build It score, and the other is the Break It score. Now, the Build It score is determined according to good performance, extra features that are provided, but it's harmed if bugs are found and exploited by Break It participants. Now, on the flip side, the Break It score is higher the more vulnerabilities you're able to find. Now, in addition to trying to be a fun and educational contest, Build It, Break It, Fix It aims to be a scientific experiment. It tries to show what works. In particular, there are many ideas for improving computer security, but few of these ideas have been put to any sort of scientific test. The contest sets up an experiment where it tries to measure the impact of the choices you make during building and breaking in terms of the ultimate outcome. Did you win the contest? Did you avoid security vulnerabilities? If you're a breaker, did you find lots of security vulnerabilities? In other words, we can look at data after the fact and try to see what it says about what works. Now, why am I talking about this contest at CSF? I believe that Build It, Break It, Fix It is a complement to foundational security work that often appears here in terms of security properties, programming languages, tools, analyses, and more. Oftentimes, this work is forced to deal with the fact that there is no perfect solution. For example, non-interference is talked about quite a bit. It's great, but it basically never holds. As such, developers and system designers are forced to make trade-offs. For example, data needs to be declassified while most of it hopefully does not contribute to a security leak. Evaluating these trade-offs is hard to do mathematically in a foundational way. So one alternative is to look as a practical matter at how they play out empirically. And Build It, Break It can help with that. So over the past several years, we've run several contests and we have carried out this scientific experiment and we've looked at the results. 3 contests were carried out between 2015 and 2016 with 156 different teams participating. 134 were part of a Coursera online class that we held. The rest were university students throughout the US and the rest of the world. And several interesting trends emerged from this data. The most significant was that programming in C and C++ benefits performance, but it significantly increases the chances of a security vulnerability compared to the use of a type-safe programming language like Java or Go or Haskell. Other interesting results were that smaller code tends to do better, larger teams do better both for Build It and Break It, more coding experience does better for Break It, and knowing more languages, programming languages, tends to help with Build It. In addition to looking at just the extensional data, we looked at actual submissions to see if there were any trends there. In particular, we looked at a sample of 94 of those 156 projects and identified 182 unique vulnerabilities based on exploits submitted by contestants, but also problems we noticed ourselves. Doing something called axial open coding, different individual reviewers were able to come to agreement on different things that they saw and noticed several trends. First of all, they noticed that simple mistakes were pretty rare. Only about a fifth of the overall projects had these sorts of mistakes. On the other hand, vulnerabilities due to misunderstanding of security concepts were very common. Almost 4/5 of the overall contest submissions had such a problem. And these owed to unintuitive security requirements, for example, integrity or replay versus confidentiality, and conceptual errors, for example, failing to understand the importance of the use of randomness. These results have implications for how we could construct better APIs or programming patterns and maybe better tools and documentation. So in this talk, I'm going to tell you more about build it, break it, fix it, and these results. But before I do, I want to encourage you to go to our website and look at the code and consider downloading and running a contest yourself. Several other universities have over the past several years, and we often run build it, break it, fix it as part of our security class at the University of Maryland. All right, so I'm going to tell you more about how the contest is set up. I'm going to tell you more about those results that I just previewed, and then I'm going to tell you more about future ideas and research that could follow on. All right, so recall that build it, break it, fix it is composed of 3 rounds, and the first round is the build it round. This is the round in which participants build software or code according to a posted specification. So they aim to make it correct, featureful, efficient, and secure. And most of these things, the first 3, are assessed by test cases that we, the organizers, provide. And security, of course, is tested by round two participants during the break it round. For many elements of the build it task, it's up to the participants what to do. They get to choose the design of their software. They can choose which optional features to implement. They get to choose which programming language to use and which testing tools to use. And they get to decide how to divide the task amongst their various team members. Now, in the break it round, each team has access to the other team's submissions, and they get to look at it and attempt to find bugs and vulnerabilities in those submissions. So they are given access to the source code, and they're given access to a virtual machine which can run all of the contest submissions. Once again, how the participants do this is up to them. They can divide the task up as they like, use different tools, code reviews, analyses, and so on. The final round is the fix it round. During this round, exploits submitted by break it teams are made available to build it teams, and the build it teams can try to fix bugs to show that many different exploits, test cases, are exploiting the same underlying bug. So for example, this is how this could happen. If we have a function that's subject to a buffer overrun, so here the stir copy could overrun buff, there are many ways that this buffer overrun could be made manifest. For example, by passing this string, which is more than 10 characters. But of course, this string and this string are more than 10 characters as well, and will exploit the same buffer overrun, even though they're different strings. So build it teams should not lose points for each of these exploits. Instead, they should only lose points for the bug itself, that is the buffer overrun. To show that each one of these tests is in fact evidence of the same bug, build it teams are able to fix that bug. So in particular, they could replace stir copy with strl copy, therefore preventing the buffer from being overflowed. And now all of the tests should not fail anymore. Now, of course, it's possible that a team could fix a bug, which in fact is multiple bugs. And we leave that to judges to decide whether the fix is a single fix or multiple fixes. If it's multiple fixes, it's disqualified, and the build it team will not gain the points back. So in sum, the breaker score is determined based on the number of bugs found, and these bugs there are more points for security bugs as opposed to memory safety violations that are not exploited versus just correctness bugs. But those bugs need to be shared with all of the other break it teams that also found it. So this motivates trying to find more and difficult bugs that other teams will not find, which of course encourages greater coverage of build it code and hopefully finding as many bugs as possible in that code. On the flip side, the builder score is going to take into account those correctness and performance tests from the first round, but it's going to lose points for bugs found by break-it teams, but of course it might gain some points back if it turns out that multiple exploits are evidence of the same bug. So roughly speaking, this is the way the score progresses over time. We can see the y-axis here is the build it team score, and the x-axis is the date. So during that build it round, each of the individual team scores starts to move up as those teams pass more and more correctness tests. But during the break it round, those scores go down as break it teams find exploitable bugs and vulnerabilities in the submissions from the build it round. And then finally, during the fix it round, teams get some points back as they fix those bugs and show that, in fact, multiple bugs are the same. Now, Build It, Break It, Fix It has been live on the web since for at least 5 years. You can go to builditbreakit.org to check out the site. Just a few notes on how it's implemented. Our Build It, Break It infrastructure is based on the YESID Haskell-based web framework. And we actually implemented an extension of labeled.io, LIO, a extension of the Haskell IO monad, which aims to support label-based security enforcement. Our extension supports web-based development. We showed, in fact, how our extension is secure in a mechanized development in Liquid Haskell, which we presented in POPL 2019. In case you're curious, you can check it out. All right, so let me tell you about some of the contests that we've run so far. The first one was asking participants to implement a secure log. And what do I mean by that? Well, the log is going to contain a bunch of records, and it represents sort of a security system at an art gallery. So for example, this log append command is saying that Bob enters a gallery at time 8 a.m. This log append command says Alice enters the office at 8:01. And this one says that Alice exits the office at 8:15. Now, all of these log append commands require providing a key that was used to create the log. The very first log append command creates the log, and all subsequent commands need to provide that key. So this log read command also provides the key, and it can ask, for example, what rooms Alice has been in according to the log, and the answer being, of course, the office. Now, what are our security requirements here? Well, the adversary is going to have access to the log. It's able to look at its contents and, in fact, manipulate them, but the adversary is not able to see the key. The security requirements, the break-it teams to show a security bug need to provide an exploit. And the way that that works is that the contest generates logs according to each build-it team's code. So if there's 20 build-it teams, there may be 20 distinct implementations. And so the infrastructure will generate, say, 100 random logs for each of those 20 implementations and provide them without a key to the break-it teams. Now, the break-it teams then can, based on their examination of the code, for example, show that integrity can be violated by changing the log to attest to a false fact without having that change detected. And likewise, can violate confidentiality by showing that the break-it teams know some fact about the contents of the log despite not having the key. We limit in this particular contest submissions of each kind of bug because even though there may be multiple bugs, multiple things that could be exploited, we can't tell if individual exploits are using, say, vulnerability A or vulnerability B, and so we conservatively allow one of this sort of security bug to be reported. All right, so the next contest is what we call the ATM contest. It's a secure communication problem. And what happens is each of the teams implements a server, which represents a bank, and a client, which represents an ATM. And the idea is that the ATM communicates with the server, providing a so-called authentication token to confirm that it's communicating with the actual server. And it provides a card, which is like the PIN, to go along with the user and transaction request. So in this particular case, Bob is establishing a new account with $1,000, providing his PIN to establish that account. Now, subsequently, Bob can connect to the bank, provide that PIN once again and say deposit $50, or then later on withdraw $600. Now, all this time, the adversary is able to observe communications between the client and the server, and of course could manipulate those communications in some way or otherwise learn information from them. And also the adversary could masquerade as a client trying to confuse the bank and getting it to reveal private information or maybe corrupt that information. So to test the security, break-it teams can implement a man in the middle, which sits between the client and the server. And the man in the middle program is allowed to script a command server to direct the ATM to send commands. The man in the middle can then observe those commands and perhaps manipulate the messages that are going back and forth between client and server to try to create an exploit in some way. This exploit's success is tested against an Oracle implementation, and if the outputs differ in some way, then that's evidence of the exploit. So to give you an example, here's the man in the middle program, maybe that's provided by one of the break-it teams. The man in the middle could tell the command server, okay, please instruct the ATM to initiate a deposit message. The ATM then does that message. The man in the middle can intercept the message, despite it being encrypted, for example, and then relay it, but then say relay it again, trying to do a replay attack and thus duplicate the deposit. If the query balance succeeds, that is, it finds that there are $2,000 and not $1,000 in the account, then that's going to differ than the Oracle, which will block replay attacks, and therefore there is evidence of an attack, of a vulnerability. The last project is the multi-user database project. And the idea here is to implement a key value store that interprets programs written in a domain-specific programming language. So this language identifies the running principal and a password, and then it can create variables, such as in this case, message, and also identify permissions on those variables for access by other principals. So for example, here it creates the message that it stores on the server, but of course it's only available to the administrator until the administrator sets the delegation privilege to say that Alice is also allowed to read this message. Subsequently, Alice could log in, providing her password, and try to access message. And because she's been granted access rights, she'll be able to read it. Now, in this case, we're not worried about communications. We rule that out as an attack vector. And instead, we just consider the case of a malicious client that might try to confuse the server into corrupting data or revealing data that it shouldn't. In this particular case, an exploit is a query sequence that's sent to the server, and privacy is considered to have been broken if the Oracle would deny access, but the target allows it, and integrity is the dual, write access is allowed. It is denied by the Oracle, but allowed by the target. And availability if it's the reverse, if access is denied, but the Oracle would succeed. Another availability violation is when the target program just hangs or crashes or something like that. And there's no limit on security breaks for this particular contest because we can distinguish different vulnerabilities in this case. We know which vulnerability is being exploited, but the overall number of breaks is more limited. Okay, so as I said, we ran this contest, the programming contest for these 3 problems. And what we wanted to do is look at trends amongst all those different problems in the different contest instances to find out what correlates with success and failure. And to do that, we did a linear and logistic multiple regression over the data. We looked at 4 statistically significant factors that correlate with outcomes of interest. For example, and those are listed here, the number of team members, languages, coding experience, language type, number of lines of code, and whether or not they were part of the MOOC or university participants. And we correlated those factors with outcomes on the build it and break it side. So the build it was the SHIP score, that is correctness and performance score, resilience score, which is score after bugs scores have been subtracted, and also just the likelihood of whether a security bug was there. And on the break it side, we looked at break it score prior to fixing, and we also looked at total security bugs found. Now, because we're doing a logistic and linear regression, we're trying to tease out the independent contribution of each of these parameters. And so while some of them may correlate across all of the different parameters and all the different contest values, we're trying to see what the individual contribution might be. So before we look at some of the regressions, let's look at some of the demographics of the contests overall. So as I said already, there were 156 teams. They had an average, each participant had an average of 9 years of programming experience. And that's because many of them were part-time professionals that had been programming for a while. Many were university students, so they didn't yet have a CS degree, computer science degree, but they did have programming training. Most of the participants were part of our MOOC. The average team size was around 2, and participants were from all over the world. Okay, so let's look at the feature of language category. This chart shows the count by language of particular categories. So we looked at statically type-safe languages like Scala or C# or Java or Go. There were 49 of those in total. We looked at dynamically typed, such as JavaScript or Rust, JavaScript or Perl or PHP. There were 60 total here, but the lion's share of them were Python. And then finally, in its own category of statically typed, but only weakly so that not type safe, are C and C++. And there were 21 of these implementations. Okay, so let's look at our linear regression for SHIP score. So the coefficient column here is how those factors that are listed in the first column contribute to the total score. The first line, where the dashes are, is the baseline, and the next 2 lines are the difference to the baseline. So in the group of columns that I have highlighted, the baseline average score is for the C and C++ category. And you can see here that choosing to program in a statically or dynamically type-safe language reduced your SHIP score by 112 or 133 points on average with statistical significance. Okay, so the boost is almost entirely due to performance benefits. This is something we looked at, not due to optional features. Also shown in this chart are some weaker effects based on the number of languages known and lines of code, where they're hovering around statistical significance, but they don't dominate quite as nearly as much as performance. Now, we also looked at the likelihood of a security bug. We used log likelihood, so that X coefficient there is 1 over the likelihood. It's the difference in likelihood from the baseline. So what we see here is that using C and C++ increases the security bug likelihood by 11x. That is 1, the baseline, divided by 0.089 is 11. So it's 11 times more likely, if you're using the baseline, C and C++, that you'll have a security bug than if you're using a statically typed language. So this is a pretty sizable and significant effect. There were other weaker effects that correlated with the likelihood of a security bug, such as the number of team members, knowledge of the C programming language, and the size of your project. Now, looking at that result a little bit more closely, we can see here the percentage of programs that had a security bug according to language. And you can see that for the contests, the spring, fall, and fall, which is to say the log, the ATM, and the multi-DB problems, the log had 5 out of 9 C and C++ projects had a security bug, where 7 out of 7 and 5 out of 5 did for the next 2 contests. Whereas for the other language categories, the likelihood of a security bug was lower. Now, your first thought might be that the reason for the difference is C and C++'s lack of memory safety. That is, there were more crash defects. But in fact, that's not the entire difference. 8 out of 17 of those projects had no crash defects, but they had a security bug for other reasons. They misimplemented access control, for example, or they used the wrong amount of randomness. They didn't use encryption, something like this. It wasn't just exploitability based on buffer overruns. Okay, so now I'd like to turn to the qualitative assessment. We didn't just look at the final outcomes and data analysis. We also looked at the code itself. And to do that, as I mentioned at the beginning, we took a sample of those 156 projects and looked at 94 of them. We looked at breaker-identified exploits, and we also looked at the code for problems that maybe breakers did not specifically exploit. And we found 182 distinct vulnerabilities. We used iterative open and axial coding. We had 2 or more independent coders develop a so-called code book for classifying the different sorts of vulnerabilities in various ways. And the independence of those coders helps give us assurance that their high level of agreement means that other coders would probably interpret these vulnerabilities in the same way. So just to give you a taste of some of the things that we found, it was not uncommon, sad to say, that no security at all was implemented. So for example, for the log, rather than actually use encryption, some people just used Java serialization, or even just stored it as plain text. That they we didn't tell them to use cryptography, we just told them that the adversary would have access to the log, and they failed to appreciate that that meant they ought to encrypt the log. A more subtle bug was that sometimes teams encrypted individual records, but did not globally encrypt the log. For example, maybe they didn't have a hash over the entire log. And what that meant was they were able to duplicate or modify or remove individual records and therefore violate integrity that way, even though those records, say, individually were kept confidential. For the ATM problem, it was common that randomness or secret size were too small. It was also the case that replay messages were very common. No nonces were included in those messages. For the multi-user database problem, users needed to implement this delegation role-based access control policy, and they often mess that up in various ways, in particular in dealing with delegation chains. Sometimes there would be time of check, time of use failures. Sometimes there was a failure to do certain sorts of checks due to code duplication. Basically, it was a failure to implement the security policy as specified. So I can't show you the whole code book, but I can give you some summary observations. One was that no implementation and misunderstanding of security requirements were more common than mistake. That in reading the requirements for the specification, it was more likely that people would mess up something, fail to implement it, or misunderstand the way to implement it successfully than to implement it successfully, but to maybe make a mistake. So-called unintuitive requirements were missed or implemented incorrectly more often. So by unintuitive, I mean integrity protection. It's well known that integrity is harder to understand than confidentiality. For example, with the log, that issue of needing to hash the entire log, that happened very often, whereas the failure to encrypt entirely was far less common. Replay attacks, also unintuitive, were very common. Another trend we saw was that complicated implementations often bred mistakes. So if people did not streamline their implementation or have a small trusted computing base or create a library rather than to inline lots of code, very often they would make a mistake, sort of get it right 4 times out of 5, and then that mistake was exploitable. And indeed, those mistakes were readily exploited in the contest. Okay, so I want to step back and summarize the results that I presented to you so far. First, of the data analysis, it was statistically significant that performance correlated with coding in C and C++. People tended to have higher scores than if they used a statically or dynamically type-safe language. But there was a lower chance of a security flaw if the program was programmed in a statically type-safe language as opposed to C and C++. So the nice thing about this is that it shows in an extensional, empirical, sort of well-designed experiment, kind of the common wisdom that we already have, that programming in C and C++ will improve your performance, but it creates greater risk. What our contest does is it also shows the extent to which those things are true. That is that the performance gain is significant, it's pretty substantial, and also 11 times more likely to have a security flaw. That's a substantial risk. Now on the break-it side, I didn't talk about those results. In fact, I didn't talk about a lot of the data analysis results that we did. I'll refer you to our paper for that, or I can answer questions about it. There is an increased chance of finding a security bug if you have a larger team. No surprise, you can parallelize your work. And there's tends to be a higher overall bug count. Again, larger teams are able to do that. And so are teams that took part in the build it phase because they understand things a little bit better. Okay, so we've run these contests. We continue to run them and improve things. What have we learned from them, aside from maybe confirming conventional wisdom through this experiment? Well, one thing we've learned through the qualitative data analysis is that API design and documentation could be used to help avoid security mistakes and failures of implementation. That is, rather than have programmers use a very complicated, featureful, knob-filled API, the API should instead be designed for the programmer to do what they want, that is according to their goals, rather than to offer them lots and lots of mechanisms that they need to figure out how to string together. And the documentation should make this clear as well. Vulnerability analysis tools didn't make any difference as far as the data analysis was concerned. Teams that reported to us that they used these tools did not have any advantage in finding bugs. And this is not surprising given our qualitative results, where many of these flaws were design level flaws, not low level mistakes. So could we build better tools that would have caught some of these bugs? Are there ways that we could assess the design? Are there maybe machine learning techniques that could smell bad smells in the code that suggest a closer look is warranted, rather than the more semantic, type-based, analysis-based tools we tend to build these days? And lastly, one thing I'd really like to do is to assess the build it, break it, fix it impact on security education. My suspicion is that the reason that a lot of teams failed to do the right thing was because they have been told about the problems that could happen, but they've never experienced them. Security is very often not easily tested in a class, and there's no experience like build it, break it in most classes to sort of send home to students that they have failed to defend against replay attacks, or that they haven't done integrity protection. As an education tool, it might be that build or break it leads to a better trained, more aware category of developers. And we would love to try to set up an experiment to test that. Of course, a very obvious next step is to look at building a safer, low-level programming language like C. Right, C is fast, people want to use it. It's in 6.5 billion lines of legacy code, according to one measure I've seen. But of course, it's dangerous, 11x more so, according to our results. So right now, I'm starting to work on a project called CheckC. It's an extension to C that supports spatial memory safety. This extension includes some new types of pointers that are safe pointers. It's implemented on top of Clang and LLVM. It's open source on GitHub, and it's run by Microsoft. That's including it as part of the product. The language supports incremental conversion, and by mixing checked and unchecked types. So in this sense, it's like gradual types, for example, in a language like TypeScript, which does for JavaScript. And we're building a conversion tool to automatically add check types to your legacy C code. Now, of course, another alternative to C is Rust, and many of you may have heard of that. Type safety in Rust implies a lack of memory errors and a lack of data races, which is a great help to security. And it's got low-cost abstractions with no garbage collector, with, therefore, competitive performance with C and C++. So the question is it a viable practical alternative to C and C++? And to try to explore that not from a technical perspective, but like the contest, a more empirical, qualitative perspective, we have started to carry out interviews and surveys to study the question. Okay, so that's all I have to say for today. I'd like to thank you for listening. This has been about the Build It, Break It, Fix It security contest, which aims to encourage participants to build secure software, not just to break it. And through the contest, we've carried out a scientific experiment that allows us to analyze the results of the contest to see what works. What we found is many interesting things correlate with security success and failure, and there are lots of new things that we can do next. And I encourage you to check out the site and the code, and I look forward to your questions. Thank you.